Welcome back to the Deep Dive. Today, we're talking about something that is absolutely fundamental if you're building anything, and I mean anything, substantial in Google Cloud Platform.
Yep, you got to nail the networking.
Exactly. We're talking about the core infrastructure,
Mm.
the stuff that defines isolation, security, and how everything communicates.
It really is the foundation.
So today, we are undertaking a pretty critical deep dive into virtual private cloud networks, or VPCs, and their subnets.
And, these concepts aren't just little checkboxes you tick on an architecture diagram. They are the entire bedrock of your cloud house.
That's a great way to put it.
And Google Cloud's networking model is, well, it's subtly, but also fundamentally different from its competitors. Getting your head around those differences is, I think, the key to designing efficient, scalable, and most importantly, secure cloud applications.
Absolutely. So for anyone listening, maybe try to think of a VPC network as creating your own private data center. It's logically isolated from everyone else, but, instead of sitting in some dusty server room in Tulsa, it's seamlessly integrated into Google's massive, low-latency global network.
It's your infrastructure, completely defined and managed by software, and it lets you treat global resources as if they were literally plugged in right next to each other.
So our mission today, and to solidify that foundation for you, we need to cover the VPC's unique global nature, which is a big one.
Huge.
We'll also need to understand why the custom VPC is really the only choice for production environments, and then we'll break down some of the more complex configuration mechanics, like things like secondary IP ranges for Kubernetes.
Right. At the end of the day, a VPC gives you this really granular control over 4 foundational elements of your cloud environment. First, the IP address arenas where your resources actually live.
Okay.
Second, the routes that traffic uses to get around. Third, the firewall rules that, govern who can talk to whom.
The bouncer at the door.
Exactly. And fourth, the specific access controls for managing that network. So yeah, let's make sure you know how to wield that control effectively.
All right, let's get into it.
Let's do it.
So I think we have to start with the single most critical difference between GCP and really other cloud models. It's the one that usually causes the most confusion when people migrate.
Whoa, for sure.
The scope of the network. The VPC itself is a global construct.
It is. And this is the hill we really need to define very, very clearly. A VPC network in Google Cloud is fundamentally defined as a global resource. Meaning it's not restricted to any single region like a central one or Asia East 2. It just exists as this single entity, this one container, that spans Google's entire global network.
So why? Why did Google choose that global approach? I mean, when you think about it, things like compute and storage, they're inherently regional. So making the network global feels, a little counterintuitive at first.
I can see that. But the primary driver is really simplicity, performance, and of course, security. Because the network itself is global, the moment you define that VPC, you've essentially created a private, unified network namespace across the entire planet.
And it's all linked by Google's own private fiber backbone.
Exactly. Not the public internet, their backbone.
Okay, so spell out the significance of that for me. What's the real-world impact?
The significance is it's profound, especially when you think about latency and security. So let's say you launch a back-end database in, Europe West 3 in Frankfurt.
Okay.
And then you launch an application server in US East 4 in Virginia.
Thousands of miles apart.
Thousands. But because they're in the same global VPC, they can communicate privately using their internal IP addresses. That traffic never, ever touches the public internet. It just zips across Google's dedicated high-speed backbone.
So you're saying we get the benefit of geographic redundancy, maybe putting services closer to our users, but we do it without the security risk or the latency penalties you'd normally get from routing traffic over the external internet.
That is the massive architectural advantage right there.
Wow.
And I think about the impact on internal DNS resolution, too. Resources globally within that single VPC, they can just resolve each other's host names and internal IPs seamlessly. You don't have to manage all this complex cross-region peering or external routing just to get 2 VMs in different continents talking to each other securely.
Okay, that makes sense. So the VPC network container, that part is global. But the infrastructure, the VMs, they still have to live somewhere physically. So where does the regional control come into this picture?
And that's the perfect question. That is the definition of the subnet. So we have to contrast the global VPC network with the subnets, which are strictly regional resources.
Ah.
The subnet is that specific localized component that defines the block of IP addresses where your resources actually get to live. When you launch a VM, you absolutely have to choose a specific region and a specific subnet within that region.
So the VPC is the global skeleton.
Yes.
And the subnets are the regional IP-defined organs. You can't have a subnet that crosses regional boundaries, that enforces the physical placement rule.
Precisely. So if you use a single VPC to span, I don't know, all 30-plus GCP regions, you just manage 30-plus distinct regional subnets inside that one global container.
Got it. Okay, let's quickly reiterate those core attributes of VPCs that make them so flexible. We mentioned isolation, but let's talk about why it's so strong.
Well, isolation just means logical separation. Your resources can communicate privately, and they're separated not just from the public internet, but also from other VPC networks, even ones that belong to your own organization, unless you explicitly connect them with something like peering.
It's like a software-defined air gap.
That's a perfect analogy.
It is.
It is.
Then there's the flexibility we get from controlling the addresses.
Yeah, the flexibility. You, the user, define the specific IP address ranges, the CIDR blocks that you want to use. You define custom routes. You define granular firewall rules. This just gives you absolute control over your environment, which is, essential for compliance and for any kind of customized scaling.
And finally, connectivity.
Connectivity is the key to hybrid cloud. VPCs are designed from the ground up to integrate. Whether you're linking to another GCP network with peering, or connecting to an external cloud, or spanning that divide to your own on-prem data center with Cloud VPN or Interconnect, the VPC is always the hub.
Okay, so let's bring it back to the listener. Why is it so crucial for them to understand this global versus regional split, especially for, architects who are designing their first large-scale system on GCP?
It's crucial because it radically simplifies your network topology. I mean, if you come from an environment where networks have to be regional, your first instinct might be to create, say, VPC US Central and VPC Europe West.
Right, you'd replicate what you already know.
Exactly. But in GCP, that's just redundant overhead. The optimal design is often one large, globally scoped custom VPC, and then you just leverage regional subnets to place your services close to your users.
And that saves you what? The administrative burden of managing a bunch of different network configurations?
That, and it immediately gives you that high-performance, private, inter-region communication we were talking about. It's the most efficient way to achieve a global footprint.
Okay, that's a fantastic foundation. So we know the VPC is global and the subnet is regional. Now let's talk about the different flavors of VPCs you get, because there's sort of the quick start version and then there's the serious production version.
That's a perfect way to put it. We have the default VPC networks and the custom VPC networks.
The default VPC network. This one is designed for speed, right? It just appears when you spin up a new project.
Yeah, it does. It's automatically created for every new GCP project, and it's really meant to be a quick sandbox. It's great for testing, maybe exploring a new service, or just, learning the basics without having to worry about defining IP address ranges right away.
Okay, and what does that default configuration actually look like under the hood? What do you get?
You get a full configuration. It automatically provides pre-configured subnets in every single available GCP region globally, and each of these subnets is provisioned with a 20 CIDR block.
A 20 is, what, about 4,000 IP addresses per region?
Roughly, yeah. And all of those 20 blocks are drawn from this one massive 10.128.0.09 address range that Google sets aside.
That's a huge address space. I think it's roughly half of the entire 10.0.0.08 private range. So, okay, it's ready to go immediately.
Yeah.
But this is where the security alarm bells start ringing for me.
They should be.
Why can't I use this for my serious production-grade application?
The security caveat is, it's overwhelming. And it all comes down to the default firewall rules. The default VPC is, I would say, fundamentally insecure for production because it comes with highly permissive firewall rules already configured.
Permissive how?
Well, these rules include things like allow internal, which is fine, that lets your VMs talk to each other. But crucially, it also includes allow shish, allow RDP, and allow ISIMP ingress rules from 0.0.0.000.
Well, okay, let's be very specific about what 0.0.000 means to a security architect.
It means the entire public internet. It means anyone, anywhere, By default, the default VPC allows the whole world to attempt to connect to your resources on common administrative ports like TCP/22 for SSH and TCP/3389 for RDP.
So even though you'd still need, a valid key or a password to get in, you're basically putting a welcome ad out for attackers to come and try to break down the door.
You're inviting them to try, and exposing those ports to the world violates every modern security standard out there.
It's a clear violation of the principle of least privilege right out of the gate.
Mm-hmm.
You are granting far, far more access than is needed for anything to function.
Exactly. And that leads us, thankfully, directly to the custom VPC network, which is the required production standard. It's what you should be using 99% of the time.
And what's the difference?
When you create a custom VPC, you start with a completely blank slate, a clean sheet of paper. You, the user, have to explicitly define every single IP address range, every subnet, and crucially, every single firewall rule.
So the immediate security benefit there is that a custom VPC starts with most restrictive setting possible.
Deny all.
Deny all ingress and egress traffic by default. And you only open the specific ports and protocols that are absolutely necessary for your application to function.
Precisely. This aligns with the least privilege concept perfectly, and it also enforces another key principle: separation of duties. It means the network administrator has to explicitly and consciously define the secure boundaries, rather than just inheriting some permissive default setting.
So for our listeners who are focused on, say, the professional cloud architect certification, that's your critical takeaway, right?
Yeah.
If a question asks for a secure, production-ready environment,
The answer is always, always to create and deploy a custom VPC. No exceptions.
always. Okay, let's make this more concrete. Let's look at why this granularity matters, using a very practical, common example. A standard 3-tier architecture.
Perfect example.
So in a typical setup, we need a presentation tier, our web servers, an application tier, and a data tier, our databases.
Right. So in a custom VPC, you achieve this network segmentation by creating 3 dedicated isolated subnets. We could call them, say, web subnet, app subnet, and DB subnet. These could all exist in the same region, or they could be globally dispersed. But the point is they are logically separated.
And the firewall rules. They become the bouncers at the doors between these different segments.
Correct. You'd use very strict firewall rules to ensure a few things. 1, only the public load balancer can reach the web servers in the web subnet, and only on port 80 or 443.
Standard web traffic.
Standard web traffic. 2, the web servers can only talk to the application servers in the app subnet and only on their specific application port, let's say it's port 8080.
Oh, yeah.
And then, critically, in number 3, the application servers can only talk to the database servers in the DB subnet and only on the specific database port, like 5432 for PostgreSQL.
And I'm guessing the most important rule here is the one that denies direct access to that database from anywhere else.
Yes. You must have a rule that ensures no direct external traffic and no internal traffic from the web tier can ever reach that DB subnet. This simple segmentation is what prevents lateral movement if, say, your web tier gets compromised. The attacker is stuck there.
They can't just jump directly to the database and exfiltrate all your data.
They're contained.
Okay, let's amplify this with the hypothetical healthcare scenario you mentioned, something requiring high-pablo compliance. This isn't just a best practice anymore. It's a legal and regulatory requirement.
It's completely non-negotiable for highly regulated data. If a healthcare company is storing protected health information, PHI, they absolutely must use a custom VPC. They would define their database subnet where the PHI is stored with the strictest possible rules imaginable.
So walk me through that required firewall flow. What specifically makes it compliant?
Compliance is really achieved by ensuring that data is inaccessible by default. Their custom VPC firewall must enforce that the database subnet only accepts ingress traffic from the explicit internal IP ranges of the application servers. Not even the whole app subnet, but the specific IPs of the servers.
Wow, that granular.
You can get that granular, and furthermore, that traffic is restricted to only the database port. No SSH, no RDP, no IC, ICMP, nothing, and absolutely no traffic from any network outside of that trusted application tier. This is how you guarantee that PHI is shielded at the network layer, even if an attacker somehow gets credentials for, say, an external jump box.
They still can't get to the data.
They can't. That level of granular control is just, it's impossible to guarantee in a default VPC environment.
Okay, we've firmly established that the custom VPC is the only choice for any serious architecture. So now let's roll up our sleeves and look at the actual build process, starting with that that unique GCP distinction in how we define the IP space.
Right. So when you go to create a custom VPC, let's give it a name, say Enterprise Production-VPC, you're basically just creating an empty envelope. You give it a name, and then you select the custom subnet creation mode.
And this is where the GCP model really diverges sharply from other clouds.
Yes, this is a key point. In AWS or Azure, you often start by defining a single, massive, classless inter-domain routing or CIDR block for the whole VPC, something big like 10.0.0.016.
And then you chop it up.
You then carve smaller subnets out of that big block.
Yeah.
In GCP, when you create that custom VPC container, that envelope, you do not define a global CIDR range.
So the IP ranges are only defined when we get down to creating the regional subnets. Why is that flexibility better? It seems like a small detail.
It seems small, but it radically simplifies IP address management, especially when you start thinking about connectivity down the line. Since the VPC itself has no predefined global range, you completely avoid the risk of IP address overlap when you eventually want to peer this VPC with another network.
Ah, like a partner's network or an on-premises data center.
Exactly. You can selectively define unique, non-overlapping ranges on a regional basis, tailored specifically to what you need in that region, rather than being stuck with some massive block that you defined 5 years ago and now conflicts with the company you just acquired.
That flexibility is crucial for long-term scalability and avoiding network friction. Okay, so after we name the global container, we immediately move to the regional configuring subnets phase. What are the non-negotiable requirements there?
Every subnet creation requires 3 things. First, a unique name. Second, you have to select the specific region. It must be regional. And third, you have to define the primary IP address range, which must be a unique CIDR block within that VPC, like 172.16.1.024. This is the space where all your standard resources, your VMs, will get their internal IPs.
Okay, now let's talk about a more complex feature, but one that's essential for modern containerized architecture: secondary IP address ranges. If the primary range handles our VMs, what on earth is the role of the secondary ranges?
This is a bit of a deep dive within a deep dive, and it's absolutely crucial for anyone running Google Kubernetes Engine, GKE, at any kind of scale. Secondary IP ranges are used almost exclusively for GKE VPC native clusters.
VPC native. And what are we trying to achieve by defining a whole separate range?
Segmentation and superior routing. See, a GKE cluster actually uses 3 distinct IP ranges. There's one for the node machines, the VMs, which is taken from the subnet's primary range. But then you need a range for the Kubernetes pods themselves, and a third one for the Kubernetes services. The secondary ranges are what you use to define the address space for those pods and services.
Okay, but why not just use the primary range for the pods too? It seems simpler.
It seems simpler, but if you force the pods to share the primary range, you can rapidly exhaust your address space. I mean, you can run dozens of pods on a single node. By using secondary ranges and a feature called alias IPs, GKE can assign unique IP addresses directly to the pods.
Okay, and that's the key part.
That is the key. These pod IPs are now known to the underlying VPC network. They're natively routable across the entire VPC without requiring any complex network address translation, or NAT.
That's significant. Routable pod IPs mean what? Improved debugging, better network observability.
Yes, and most importantly, seamless integration with services outside the cluster. Your pod can talk directly to a Cloud SQL database or another VM just using internal VPC routing. There's no translation layer in the way.
That's a huge deal for performance and simplicity.
Exactly. Alias IPs are what enable this efficiency. It allows you to run tens of thousands of pods, each with its own real routable IP, without burdening the node machines or adding complexity to the cluster networking layer. It's really the definition of how you scale container networking inside a VPC.
That's a fundamental piece of GKE networking architecture that I think often gets overlooked. Okay, moving back to the primary range definition, we need to talk about the addresses we can't use, the rule of 4.
Right. Every single subnet, regardless of its size, whether it's a tiny 24 or a huge 16, always reserves 4 specific IP addresses for internal network functions. Let's use the subnet 10.50.1.024 as our example to make it clear.
Okay, so the first reserved address is xxstackxx.0, which in this case is 10.50.1.0.
Correct. That's the network address itself. It just defines the start of the block. You can't assign it to a resource.
The second is xxxped1 or 10.1.1.1.
This is always reserved for the default gateway. All traffic that's leaving the subnet will be routed to this address first.
Got it. The third one is x.254, which is 10.50.1.254.
This one is reserved by GCP for future use. It's essentially a hidden slot for them to evolve the network without breaking things for you.
And the fourth and final one is XButX, XButX.255, or 10.50.1.255.
And that's the broadcast address. So even in a small 24 subnet that mathematically has 256 addresses, you only ever have 252 usable IP addresses for your VMs and other resources, knowing that rule of 4 is absolutely essential for capacity planning.
And capacity planning brings us to a huge critical detail for any architect: expanding subnets. What happens when that 24 subnet with its 252 addresses runs out of IPs? Are you stuck?
Running out of IP addresses is a major operational headache, but the good news in GCP is that you can expand a subnet's primary IP range without downtime. So if your application is critical and you suddenly realize you need more capacity, you can change that 24 range to a larger contiguous block, like a 23 or even a 20.
Okay, wait. If I can expand a subnet without downtime, why should I bother with detailed planning up front? Why not just start everything small and expand later? What are the dangers or gotchas of expanding too frequently or too late?
That's a really key question. While the technical capability exists, poor planning leads to IP fragmentation and a lot of administrative complexity. The biggest danger lies in the strict restrictions on this. For one, you cannot shrink a subnet.
Oh.
Once you expand, that IP space is locked in forever. So if you expand multiple times in small increments, you end up with this fragmented, unnecessarily large subnet that might suddenly conflict with a future peering connection or a hybrid deployment you didn't anticipate.
So the ideal strategy is to plan a range that allows for maybe a single logical future expansion, but relying on it as your primary capacity management tool that's just introducing unnecessary management overhead and risk.
Precisely. Plan big enough initially to avoid conflict, but have that expansion capability in your back pocket as a safety net, not as your primary tool.
Makes sense. Okay, let's discuss another vital security feature that we toggle at the subnet level: private Google access, or PGA. This feels like a must-have for any secure production system.
Oh, it is. PGA is designed specifically to prevent your private internal resources from ever having to expose themselves to the internet just to talk to Google's own services. It enables VMs that do not have public external IP addresses to securely access Google Cloud APIs and services, things like cloud storage, BigQuery, cloud logging, you name it.
Okay, paint the picture for me. If a VM needs to download a file from a cloud storage bucket and it doesn't have PGA enabled, what would happen?
So that VM would typically need an external public IP address assigned to it, or it would have to go through a CloudNet service to reach the public API endpoints, like storage.googlelepus.com. Even if the traffic is authenticated and encrypted, you've still exposed your internal resource to a potentially huge attack surface just by giving it a public IP.
Right. But with PGA enabled on that subnet, how is the traffic handled differently?
The traffic is instead routed internally through Google's private backbone to the respective API endpoints. It completely bypasses the public internet. This significantly reduces your attack surface, and it's absolutely essential for any VM that's handling sensitive data or operating under strict regulatory compliance.
Okay, so let's use the concrete configuration example from the outline to visualize this whole thing.
Perfect. So we created our dev VPC container in custom mode. Now we need to define 2 regional subnets. We want redundancy across, say, North America and Europe.
Okay, so we'll launch Web Subnet Us in the S Central 1 region, and we'll give it the CIDR 192.168.0.024.
And then we'll create Web Subnet U in the Europe West 1 region with 192.168.0.024. And notice those are 2 completely unique, non-overlapping regional ranges, but they live happily inside the same global VPC.
And for security and for that internal connectivity to GCP services, we make sure that private Google access is toggled to enabled for both of those subnets.
And that right there is the blueprint. Global reach, specific regional IP definition, and secure private API access.
Excellent. Okay, now that our internal VPC structure is solid, let's explore how we connect it to the outside world. And that could be other virtual networks or even our physical data centers.
Right. So let's start with inter-VPC connectivity. If you have 2 different VPC networks, let's say a production network and a sandboxed research network, the primary method for linking them privately is something called VPC network peering.
And peering basically makes these 2 separate VPCs act as if they are one continuous network segment, correct? So traffic just moves between them using their internal IPs staying on the Google backbone.
That's exactly right. Resources in one VPC can talk directly to resources in the other. However, the critical administrative characteristic of peering is that the administration of each network remains decentralized.
What does that mean in practice?
It means Team A manages their VPC's routes and firewalls, Team B manages theirs, and the peering link simply facilitates the communication between them. The policies are maintained independently in each VPC.
Okay, and this idea of decentralization, it sets up a major architectural choice for large organizations. Let's dive deep into the distinction the sources emphasize here. Peering versus shared VPC. When do I choose which model?
This is a top-tier architectural question. It defines not just the network flow, but the entire organizational control structure. The core concept you have to remember about peering is that it is non-transitive.
Non-transitive. Can you explain that in a practical way?
Sure. So imagine VPC A is peered with VPC B, and VPC B is also peered with VPC C.
Okay, little chain.
A little chain. So A can talk to B, and B can talk to C, but A cannot talk directly to C through B. The connection doesn't transit through the middle VPC. You would have to explicitly create a third peering connection directly between A and C.
And if you have dozens of VPCs, that sounds like a complicated, unmanageable mesh network pretty quickly.
It's a nightmare. It's often called a full mesh, and it doesn't scale. So that tells us where peering really shines.
And where is that?
You use VPC peering when non-transitivity is acceptable, or maybe even desirable. This is absolutely essential when you're connecting VPCs that belong to different organizations.
Like connecting my GCP production environment to a vendor's GCP environment.
Exactly. It ensures true administrative separation and prevents that vendor from accidentally gaining access to your other peered networks. It's designed for decentralized teams where policies must remain strictly separate.
Okay, so conversely, what if we operate entirely within one massive corporate structure and we need consistent policies and easy centralized management?
That is the perfect use case for shared VPC. You use shared VPC when you're within the same organization, and you require strict centralized control. In this model, you designate one project as the host project.
And that's managed by a core network team.
Right. The entire network configuration, the subnets, the IP ranges, the core firewall rules, it all lives in that one host project.
And then the other teams, the application developers, where do they launch their resources?
They launch their resources from their own service projects, which are then attached to the host project's network. This achieves a crucial operational goal. The network team controls all the plumbing, and the application teams only have to worry about deploying their code into a pre-approved network segment.
So it ensures consistency, simplifies centralized quota management, and it makes life much easier than trying to manage some non-transitive peering mesh inside your own company.
Absolutely. The key decision is centralized administration. That's shared VPC versus distributed administration or external connections, which is VPC peering.
Got it. Shared VPC is for scaling inside the organization. Peering is best for external or simple point-to-point connections.
You've got it.
Okay, let's move from the virtual world to the physical world. Connecting to on-premises networks for a true hybrid cloud setup, we have two very different options here, Cloud VPN and Cloud Interconnect.
Right. Cloud VPN is the accessible, cost-effective entry point. It uses standard IPsec tunnels that are encrypted, but, and this is the key, they run over the public internet.
So what are the trade-offs there?
Well, the benefits are speed of deployment and cost. You can get a secure VPN tunnel up and running in minutes. The trade-off is performance. Since you're traversing the public internet, throughput can be variable, and you introduce potential latency from unpredictable hops around the globe. The SLA for a highly available VPN setup using multiple tunnels is good. It's 99.9% to 99.99%, but it's not perfect.
Okay. But if that variable latency is totally unacceptable and we need high throughput and absolute rock-solid reliability, we have to step up to Cloud Interconnect.
Cloud Interconnect is the mission-critical solution. This provides a direct, private, physical connection between your data center and Google's network edge. The connection is private at layer 2, which means your traffic is completely isolated from the public internet. It never touches it.
And the performance benefits are massive, I'm guessing.
They are. We're talking extremely low latency and very high bandwidth, up to 100 Gbps per circuit. To achieve this, you need to either run a dedicated interconnect or a partner interconnect.
Okay, what's the difference between those two?
A dedicated interconnect means you, or your colo provider, physically run your own cabling into a designated Google location. This is often a colocation facility known as a Meet Me Room, or MMR. You manage the physical connection, and it is entirely yours.
And partner interconnect.
Partner interconnect is where you utilize a service provider that already has a connection into Google's network. This is often faster to deploy and can be more flexible in terms of speed options, but you still get all the security and performance benefits of that private backbone connection.
So regardless of whether it's dedicated or partner, what's happening once that physical connection is established? I mean, how do Google and my on-premises network know how to route traffic to each other?
Great question. You establish a Border Gateway Protocol, or BGP, session over that connection. BGP is the routing protocol that allows the two networks to dynamically exchange route information. So you set up a VLAN attachment over the physical circuit, and then BGP makes sure that your on-premises network knows the path to your GCP subnets and vice versa. It's all dynamic, intelligent routing.
Okay, this is a lot of pieces. Let's tie this entire architecture together using the global shop scenario, or hypothetical global e-commerce company.
Perfect. So Global Shop's goal is global reach, redundancy, and centralized governance over their application infrastructure.
So step one, they create a single organization-wide custom VPC for their production environments. And inside it, they leverage regional subnets in Central 1, Europe West 1, and Asia East 1. This gives them that private inter-region communication right off the bat.
Right. Step two. They need their core production systems to integrate with their isolated, very sensitive analytics platform. Now, since the analytics platform is managed by a completely different corporate department with its own set of policies, they use VPC network peering to connect the two VPCs.
That keeps the administration decentralized, like we talked about, while still allowing the necessary data transfer.
Exactly. And then step three. Global Shop is undergoing a multi-year hybrid migration. They're moving their legacy inventory management services from their New York data center into GCP. Latency is absolutely critical here for transactional accuracy.
So they can't use a VPN over the internet.
No way. So to solve that, they bypass the public internet entirely and use cloud interconnect. They provision a dedicated interconnect circuit, they establish that BGP session, and instantly they have a high bandwidth, low latency private tunnel linking the GCP production VPC directly to their corporate data center.
So they have successfully mixed a global VPC model with decentralized peering for internal partners and dedicated physical connectivity for their on-prem needs.
That's the complete picture.
This has been an absolutely indispensable tour of the GCP networking fundamentals. Before we let you go, though, let's quickly consolidate the key takeaways that really need to stick in your mind as you go off and design your next architecture.
Okay. First, solidify the scope. VPC networks are global, subnets are regional. That distinction defines both your physical resource placement and your internal routing capabilities.
Second, always prioritize security. Custom VPCs are the only suitable choice for production. Avoid the default VPC because it's permissive firewall rules, which, as we said, violate the principle of least privilege.
Third, remember the mechanics of how GCP does things. You define IP ranges only at the regional subnet level, never at the global VPC creation stage. This gives you superior long-term flexibility.
And finally, pay attention to the small but critical details. Things like the rule of 4 reserved IP addresses in every subnet, and the fact that while you can expand a subnet without downtime, you can never ever shrink it once it's defined.
You know, we've spent this entire deep dive defining the roads, building the lanes, and setting up all the entry and exit points for our network.
Right.
But a secure network is ultimately defined by the traffic control system you implement on those roads.
We've built this great isolated container, but now we have to make sure every single packet of data traveling inside it is actually authorized to be there.
Exactly. The foundation is set. Now, the next logical step in mastering the system is implementing network security policy. So as you move forward with configuring these custom VPCs, I want you to consider this one final provocative thought.
Okay, what's the biggest security challenge that still remains?
How do concepts like implied firewall rules, these are rules that are present even if you don't manually define them, how do they interact with your custom policies? And even more powerfully, how does using service accounts as firewall targets allow you to implement truly dynamic, identity-based network segmentation? This lets you move far beyond static IP addresses to determine who is allowed to talk to whom.
So using identity instead of just location to secure the network.
That's the next level. That level of granular security control is really the final puzzle piece in a secure, scalable GCP architecture.
That is a powerful next step. Thank you so much for guiding us through this essential topic.
It was my pleasure.
And thank you for joining us for the deep dive. We hope this gave you the comprehensive, detailed understanding you need to master VPCs and subnets in Google Cloud. We'll catch you next time.